Hi, and welcome to the third of 5 sessions in our series on sense-making. I'm Diane Johnson, a regional teacher partner with Penzer, and I'm excited to facilitate the deepening of your understanding of sense-making in science. Our focus question for this session is, how can I use phenomena to support students' sense-making? Science ideas are the what of sense-making, and phenomena are the why, as we will explore in this session. Let's take a minute to review some important takeaways from the first 2 sessions. As part of video 1, we distinguished between an information frame and a sense-making frame for science instruction. We will explore how to select and use phenomena to promote students figuring out in this video. Phenomena are the something students are figuring out. As we saw in session 1, using a sense-making frame for instruction is congruent with our current understanding of how we learn, which is depicted in this model from McCrell. Notice that step 1 is to become interested, which is one of the purposes for using a phenomenon to drive learning. And maybe more importantly, the phenomenon should foster students committing to learning, from the earliest learners, K2, through high school in our schools. Science is a way to promote learning that engages all students in complex thinking and problem solving. In session 2, we examined why it's important to be clear on the science ideas we want students to learn and how we can gain some clarity. This clarity is essential for selecting instructionally productive phenomena. It's not that we don't know our science, it's that we want to be clear on what the standards suggest for student learning. To refresh our memories, this is how science ideas, elements of the disciplinary core ideas, or DCIs, are defined by the writers of the framework in the NGSS, from which our Kentucky Academic Standards for Science were developed. The DCIs and the cross-cutting concepts are used to explain the how or why a phenomenon occurs, and a phenomenon is used to facilitate the development of those science ideas. We'll explore how in this session. We found that getting clear on the standards our students are to develop an understanding of is critical for designing student learning experiences, engaging student understanding. That clarity allows us to select more aligned curricular materials, informs instructional decisions based on understanding where our students are and their thinking with respect to where we want them to be and how we might help move their thinking forward, and helps us more accurately assess understanding formatively and summatively. Although there are many ways to clarify our understanding of the standards, I modeled a process for doing this. I provided support resources along with some other processes to consider. It's easy to look at a standard and immediately think of a topic. I use water cycle as an example. We found that our science standards are not topical, they're conceptual, and they promote developing a conceptual understanding of important science ideas. Therefore, we have to make sense of the standards in order to figure out how to help our students come to understand these important science ideas. As you recall from session 2, we recommended keeping an electronic or hard copy of your clarification of targeted standards so that you can review them prior to teaching that particular unit. Once you've done the clarification for each bundle of standards you're responsible for, you just need to review and revise the clarifications as needed. You won't have to go through this entire process each year. Clarifying the science ideas goes hand in hand with determining phenomena to support students' sense-making. As we made sense of the standard, we thought of examples we were familiar with or connections to current events or students' lives. Because you know your students' interests and local connections, you can begin to think about how students could use these science ideas to explain them. Before we begin, take a minute to gather the materials we will use in this session. They are linked in the description below. The Selected Resources document contains links to all the materials used or referenced in this segment. If you're working in a PLC, you may want to print out and cut out a set of the phenomenon card sort, the targeted DCI progressions, and the wondering questions to do the phenomenon card sort and a sequencing activity with the questions in the DCIs. There's also a digital version of the phenomenon sort if you prefer using that. And if you prefer to work on hard copies, you may want to have a pen or a pencil or a highlighter ready. In this session, we will explore what makes a phenomenon instructionally productive and how to use phenomenon to support sense making. So, is this an instructionally productive phenomenon? Question. Why or why not? How do humans change the planet? Take a minute to consider the question. Is it instructionally productive? Why or why not? Jot down the criteria that you use to decide. If you're working in a PLC, pause the video to allow each member to capture their reasoning, then share your ideas. Note commonalities and differences in your reasoning. We're going to return to this question after doing the phenomenon sort and drafting some criteria to apply. Sorting examples and non-examples is a great strategy for surfacing and clarifying our thinking. I'm going to review the steps for the digital card sorting activity and show you an example of what it looks like before you start. Again, if you're working in a PLC, you may prefer to print out the cards, cut them out, and sort them with a partner. Sort the questions into 3 categories: DCI question, phenomenon question, or an engineering question. As you sort, note the criteria you use to decide which category the question belongs. Make note of the key criteria that distinguish phenomenon questions from the DCI or the engineering design questions. If you're doing the physical card sort, you can stop the video, do the sort, and then start the video on slide 15. You'll notice that there's a slide for both K5 and 612 in the resource folder. So select the one that's appropriate for you or the PCL that you're working with. Open the slide, but don't open it all the way to presenter mode. You'll be able to drag the questions from each slide to the side, from each side of the slide to the category it best seems to belong. Does it belong under DCIs, under phenomenon, or under engineering? Again, note your thinking as you decide on the category. What criteria did you use to determine if the question was a phenomenon question or not? This is what it'll look like if you're doing the digital sort. Again, you're going to open the slide, but don't put it on presenter mode. This is going to allow you to click on each of the 18 different questions to sort and drag them under the category to which you think they best belong. And again, note the criteria that you're using to decide which criteria they belong. You may want to pause the video and do the sort and jot down your criteria. So let's think about the criteria that you generated or your PCL generated. And we're going to compare that to those that are on this STEM teaching tool number 28, which contains qualities of a good anchor phenomenon for coherent sequencing of science lessons. So read the criteria for a good anchor phenomenon on this STEM teaching tool and think about how your criteria compared, what was similar and what was different about your criteria. Think about what seems to be especially helpful or something maybe you didn't consider and now it's like, oh yes, that would be important to think about. Pause the video, take a moment to read the qualities and compare it with your criteria. or your PLC's criteria. So let's go back to this question that we started with. How do humans change the planet? Based on our thinking now, looking at the sort and the criteria that kind of surfaced from that, then refining our criteria by looking at the STEM teaching tool that provided qualities of a good anchor phenomenon. Where did you put this? Where does it go? Is it a phenomenon question, or would it be a DCI question or an engineering question? According to the researchers associated with developing that STEM teaching tool and several PD modules from which this phenomenon card sort was taken, this is a DCI question. It's too broad to be considered a phenomenon question. It does not build upon everyday or family experiences and is basically just too much for students to explain. Like, where would you stop? It's not a specific observation students could make. It's this last criterion that was an epiphany for me. It's like it has to be a specific instance, not a broad observation or a broad generalization. But a specific example, say of human impact that students could figure out and then in turn come to understand important science ideas. The phenomenon would need to be age appropriate about human impact on Earth systems and requires that I clarify the associated science ideas, consider my students' interest, and a local connection, especially for younger students. Phenomena are specific observable events that occur in the universe. If you're working in a PLC, pause the video and discuss possible phenomena that might be used to get at this disciplinary core idea question. How could you take this broad question and then come up with a specific example that students might explore and answer that would get at building these larger ideas? We've determined some criteria for instructionally productive phenomena, but I think it helps to clarify our understanding by considering things an instructionally productive phenomenon is not. The first one I had to figure out. A phenomenon is not a hook. This is something I initially thought. It was a way to hook my students, engage them, get them interested. While a good instructionally productive phenomena does this, it does a whole lot more. It drives the instruction. It's the reason we're doing what we're doing and learning what we're learning. It's not a topic. Topics like human impact are too broad. Topics don't help focus the learning and make it manageable. This next one can be a little misleading. Although we develop a driving question from the phenomenon, the question isn't the phenomenon. The phenomenon is the observable event, where observable could mean we can't see it directly, but we can see evidence of it, things like energy transfer, matter cycling, or growth. Or sometimes it may be too large or occur over a long time period or be too tiny to observe directly. So we observe data, videos, or images. A phenomenon is not a task or an activity, but using a phenomenon to drive instruction helps us select experiences students might need to figure that phenomenon out, or help us maybe craft a task that students would be using. For many of us, the activities we did in school, including at the college level, were verification labs. Our teacher, professor told us something. They may have even used what we considered a phenomenon to illustrate the science ideas. And then we do a lab to verify what we were told. Although some phenomena can be flashy or discrepant events, they don't have to be. For example, why do puddles disappear is a phenomenon question. It's not flashy or considered a discrepant event, but it can be observed and figured out using science ideas. So what are phenomena? Natural phenomena are observable events that occur in the universe, and that we can use our science knowledge to explain or predict. The goal of building knowledge in science is to develop general ideas based on evidence that can explain and predict phenomena. This second sentence, taken from the STEM teaching tool number 42, is one that really resonates with me for using phenomena to drive instruction. Supporting the transfer of knowledge is something that I think we all strive to do. And maybe your experiences have been like mine and not always successful. Using a phenomenon to drive instruction and having students or the teacher provide related phenomena that can be explained using the science ideas being developed has been much more successful for my students with respect to transfer of these general science ideas than when I didn't design my instruction this way. I think that's something that's a little bit confusing about phenomena is considering their grain size, like, just how big or what is this phenomenon driving instruction about. So probably the one we think about the most is this anchoring phenomenon, the big phenomenon that we're going to use at the unit level to drive instruction. The anchoring phenomena is used to motivate kids to engage in the learning process. And it's the thing that provides coherence to the entire unit because we come back and revisit it throughout the unit. An example of an anchoring phenomenon might be something like, how did Mammoth Caves form? That's a specific observable instance, and it takes a range of science ideas in order to answer that. And for students in Kentucky, or maybe anywhere in the United States especially, it would be something interesting to try to figure out. The next kind of step down in size of a phenomenon is that investigative phenomenon. It's at that lesson level. So we can have phenomena at the lessons that we're trying to figure out, which also lead directly back to the anchoring phenomenon to help us figure things out. They all go hand in hand. The investigative phenomenon provides evidence for students to use in developing their models and their explanations. So it's like how we're coming to understand this. Here's the observation we made. Here's our initial model of how we think this works, how it interacts, what are the components, what are the science ideas behind that, and then how we could use that to explain this particular phenomenon, leading back to the anchoring phenomenon. They're like stepping stones or breadcrumbs to guide students towards a scientifically accepted understanding. So they're kind of that next step down. When I'm thinking about like our Mammoth Cave example for our big anchoring phenomenon, maybe an investigative phenomenon might be something about observing factors that affect weathering of limestone, where I might show them just some steps or some rocks in their local schoolyard and show them time-lapse pictures of those and thinking about what's happening here. And that would be a stepping stone to understanding what's happening at Mammoth Caves. And then maybe the smaller grain size or for a different purpose would be just those everyday phenomena, things that we want to use to connect to the anchoring phenomena or to the investigative phenomena. It's not something that students are figuring out, but it's things that, oh, that's like, it's that way to help foster transfer with our students. So if I were thinking about, again, my anchoring phenomena, how did Mammoth Caves form, my investigative phenomenon, that would be looking at examples of weathering of limestone, and then maybe we might think about, well, where have we seen things like this? So it could be a sinkhole that appears in the school lot or on the school grounds, or it could be, well, where would be another really interesting place in Kentucky that we might observe this effect of weathering, something like Cumberland Falls. So these are phenomena from students' personal experience that connect the ideas being studied with the students' world. It's a way to help broaden that generalization. Oh, it's like this. It's also a way to facilitate transfer. And so I think this is one of those steps that I probably just assumed my kids were making, and I didn't really help them make this. So I think this is an important step in really generalizing from our big experience of explaining that anchoring phenomena to, oh, here are some related things that are similar to that. So what makes a phenomenon instructionally productive? This is STEM teaching tool number 42. So I want you to access that from your resources and take just a few minutes to kind of read through it and highlight what are some key things that you would pick out of this to help you explain to a colleague what makes a phenomenon instructionally productive. And then think about the standards that you're responsible for teaching. And then think of a phenomenon that, wonder if this would relate, and share an example to help determine if you think this is instructionally productive. So pause the video, access the tool, take a few minutes to read through the tool, highlighting some important ideas, things that would be important to really explaining this to a colleague, and then come up with an example of an instructionally productive phenomenon for something that you teach. If you're working in a PLC, you'll want to develop maybe like a consensus understanding of, okay, these are the really important things that we want to remember about instructionally productive phenomena as we select materials, design materials, revise materials to use in our classrooms. So maybe you came up with some ideas like this. What makes phenomena instructionally productive? They make students wonder, and they want to ask questions, like they just kind of can't help themselves. Like, what's up with that? Even our most too cool for school high school students, it catches their attention, it makes them want to figure it out. Understanding how or why the phenomenon occurs requires the use of science ideas. So what are those targeted science ideas? And if I'm figuring this phenomenon out, well, I have to come to understand those and use those to explain it. It's interesting and accessible to all students in your classroom. One of the ways you can make it accessible is supporting it with everyday phenomena, getting students to make those kinds of suggestions as well. But it's something that it's going to appeal to all kids. And maybe not every phenomenon we select will appeal to all kids all the time, but over the course of learning, we're going to come up with those. We're going to intrigue them kind of in spite of themselves. So let's take a minute to pause and reflect. Pause the video and make some notes of important ideas you want to remember about instructionally productive phenomena, as well as some of the possible pitfalls to avoid when determining a phenomenon to drive instruction. If you're working in a PLC, share your thinking and discuss how your ideas relate to the instructional materials that you're using. So we've been looking at this idea of instructionally productive phenomena and what they are. And now we want to kind of move into our second goal and thinking about how do we determine if the phenomena is going to support sense making, and how can we use it to support student sense making? So I use this particular slide a lot because I think it really helps to capture the changes that were envisioned in the K-12 framework for science education. In the past, Using this information frame of instruction, scientists and teachers just kind of pass down the knowledge of science disciplines. You need to know these things. You really can't figure something out until you know this. This is like the dogma of science. And it worked for some students, and I would be one of those students that it worked for. However, it didn't work for all students. And when we think about the sense-making frame, we're really trying to capture all kids. That's the equity component of in GSS. We want all students to come to understand these really important science ideas because they're important to them in their everyday lives for making important decisions about their own life or about citizenship decisions or voting decisions that they might have to make. And they come to understand these important science ideas by making sense of phenomena. So the students are really the ones who are acting as scientists or engineers in this sense-making frame of instruction. But that doesn't let the teacher off the hook. We really have a lot of heavy lifting that we have to do. And a lot of that goes to selecting that phenomena that students are going to be making sense of, because that's our way to really control the learning, to really focus the learning on those science ideas that we're responsible for helping students come to understand. So coming up with the phenomena, thinking about how we're going to get kids to generate those questions that are going to lead them to understanding those important ideas, and in the process, figure out that phenomenon is really the important part of the instruction today. And that's the teacher's role in this kind of flipping the way that we're thinking about instruction now based on our new standards. So let's have an experience to get a feel for how phenomena can facilitate sense making and some of the questions that you're going to want to ask yourself in selecting phenomena that you're going to use to anchor a unit. We're going to use a phenomenon that is an anchoring phenomenon from a 5th grade unit that's found on the NextGen Storyline site. NextGen Storyline is a free open source site that contains a range of units that are aligned to the NextGen science standards. They have been vetted in classrooms and revised based on teacher feedback and looking at student work. They are all phenomenon driven, and they provide a lot of support material for teachers. So this particular one's from a 5th grade unit. If you want to explore these materials further, there's a link on your selected resource document in that light purple section, and it'll take you right to the site where you can explore the units and some of the resources there. So let's look at this particular phenomenon. Make a T-chart so that you can capture your noticings and wonderings as you watch a dead badger over a 9-day period. As you watch this time-lapse recording, capture what you notice and what you wonder. Include any patterns you observe. So go ahead and make your T-chart and just be a learner. Capture things you notice and capture things you wonder. And are there any patterns? So, what are some experiences that you might have had? Something you heard, observed, or experienced firsthand that might help you think about this phenomenon of the dead badger disappearing over time. If you're working in a PLC, pause the video and quickly share experiences you've had that might help you think about this phenomenon. So, I want you to notice the questions that are on here that would be used to prompt student thinking. After they did their notice and wonder and had a share of experiences they've had that are similar, then the teacher might push their thinking and ask kids to record their ideas of what they would expect to see. Would this happen with dead plants if they fell to the ground? And would your prediction change if these dead plants or parts of the dead plants were on a different surface or in a different area? So, as this unit was taught, some ideas didn't naturally surface from just watching the badger video. So some additional questions were added to kind of push student thinking a little bit and get them thinking about that. And then that's when the driving question was added for the students in the classroom. It's like, okay, here's the question we're going to explore now. Why do dead things disappear over time? So we aren't just limited to the badger. That's our specific example we're looking at. But now we're thinking about plants and animals in this particular scenario. As you're developing the phenomena or selecting the phenomenon, anticipating questions is really an important step in determining if the phenomenon is instructionally productive and in determining what support or prompting questions you might need to use to prod student thinking. It's critical that students generate the questions that will be answered by building understanding of those disciplinary core ideas and cross-cutting concepts you targeted. You want to take time to generate potential questions and construct an explanation of the phenomenon to ensure alignment and productivity. Anticipating the questions is a crucial step in determining the storyline and sequencing the experiences. It's critical for maintaining a coherent learning experience for students. And then just being prepared, having the needed materials ready for each class period. So we're going to take just a minute and compare your questions from this phenomena of the badger disappearing over time to those of fifth graders who've experienced this particular unit. In your resource folder, there is a slide that has a list of those questions generated from fifth graders. So take just a minute and compare. Did they come up with questions that are similar to the ones you came up with? Yours may be worded a little more sophisticatedly, but maybe they're very similar to the ones students had. Did students come up with some that were maybe different from those that you asked? And you'll notice that there's a weird acronym on the second bullet. Of course, kids are going to come up with questions that we really just can't anticipate because their minds just work so differently and they just come up with, their experiences are so different. So I found that having a category called questions we will not deal with at this time was a really effective way to acknowledge those questions. It's not that they're not good questions. It's just that we're not going to be able to pursue them in the time that we have, or we wouldn't have the materials, or they're just not related to what we're working on right now. It validated the questions. It kept them posted with the rest of the students' questions. And often we would come back to those and say, well, we kind of know this, or this might be another area or a similar phenomenon that we could experience or relate some of our thinking to. I know that some teachers use like a parking lot for their questions. And some teachers just have an other category, because you want to keep those kids' questions front and center and revisit those as you move through the learning. Another thing about using instructionally productive phenomenon is that it helps us to sequence the learning, could develop a coherent pathway for students to come to understand and figure out that phenomenon. So we want to think for a minute, what science ideas or parts of ideas do students need the opportunity to develop and are used to answer these questions, those questions that were generated from watching the Badger video, and then thinking about, would this be similar for plants, or if the surface was the same or changed, or if the location was the same or changed. So to think about this, these are some materials that you're going to need. You want to access the Disappearing Badger DCI progressions using your questions or the fifth graders' questions that are in the folder. There's also a format where you can cut out those fifth graders' questions. It might make it easier to match them up to the DCIs instead of trying to cut them off of that slide, if you want to do that physical manipulation. Take a minute to either match your questions or fifth graders' questions to those disciplinary core ideas or parts of the DCIs associated with the answer or partial answer. So would the answer or partial answer to a student's question be that DCI? So match the question to the DCI. Pause the video, take a minute to do that, either with your questions or the fifth graders' questions. If you're working in a PLC, you can kind of divide up, and some of you look at the earth science standards, some of you look at the life science standards, and some of you look at the physical science DCIs and match up questions to those or partial answers to those questions. So what are some things that you noticed? Which of the DCIs, if any, were answered or partially answered by the questions? The developers of this unit targeted the fifth grade physical science standard 1.1 and the fifth grade physical science standard 3.1, the fifth grade life science standard 1.1, and the fifth grade life science standard 2.1. Would the elements of these PEs be answers or necessary to successfully answer the questions you or the students generated? So I would look under that 3-5 band. I would look at the question. The first one of the students generated was, what are those insects doing on the dead badger? And see where it might match up to a piece of an element of a disciplinary core idea. Another question, do some parts of the animal go into the soil, get washed away, etc.? So if kids were to answer that question, would this particular element of a DCI be a part of that answer, coming to understand that? And if not, if you can't find connections, then what adjustments might need to be made to that anchoring phenomenon? In this case, the badger roadkill decomposition. Or what might be some prompting questions that you could use that would kind of broaden the students' thinking or get them to answer or get them to generate questions that more of the DCI would be a part of the answer to. If you're working in a PLC, pause the video and discuss this. What adjustments might you make? How might you use this information to help you in planning the experience for students and in determining maybe probing questions or prompting questions that you might need? So how can we use these questions that are generated from observing that phenomenon to design instruction? First thing is we can look at those questions and sequence them in a way that would help students build understanding. Another thing that's really nice about this sequencing is because you've thought about this ahead of time, you can kind of think about the questions to ask students, like, well, which of these questions would be a great place to start? And then have those probing questions, prompting questions to kind of focus kids at a place that you think would be a good place to start, because we have to be prepared. We have to have the materials ready, but we want the students to have that ownership in it. So this is a way to kind of support that and then to sequence the learning so that it's coherent. What DCI part or part of a DCI would students figure out? They would come to understand this if they answered that question. So it's a way of making sure that the phenomena gets to the science ideas or the parts of the science ideas that we want students to come to understand. And then once we've done that, we can think about what are some investigations or activities that students might do to answer the questions. And these might be things that you've used in the past that you know will get students thinking, gives them those experiences, using the practices to come up with their ideas or their evidence that they're going to use to build towards that explanation. It also might help you select experiences that students are going to need instead of just everything that's out there about decomposition and cycling of matter in a food web. It may help you really be selective about the kinds of experiences that students need, or select the kinds of instructional materials that might do that as well. So let's think about some considerations for selecting an anchoring phenomenon, the one that's going to drive that unit of instruction. To start with this, we begin with those targeted science ideas, those disciplinary core ideas. That's what we want to have students use to explain the phenomena. So we look for a phenomena that will generate questions that requires those targeted science ideas to answer. So they go hand in hand. The next step might be in sharing that phenomenon with a colleague or friends or family members. My grandsons have experienced this many times. When I think about a particular phenomenon, I want to see what kinds of questions it would generate. And since they kind of span different grade bands, I use them to kind of, well, tell me what you notice and wonder, and I can kind of fine tune it from there and come up with prompting questions. And does the explanation of the phenomenon require those science ideas you targeted? So those are some key considerations for selecting the phenomena and then seeing if that phenomenon is going to work to get at the science that you want students to understand. In your resource folder, and there are links to these as well on your resource document, are a couple of different resources that you can use to help you think through that phenomenon. There's one from the ASET group, which is kind of a collaborative of universities that have been working on support materials for developing or revising instructional materials based on the next gen science standards. And the phenomenon tool is just a series of questions, very similar to those questions or those statements that were on that STEM teaching tool number 28 that you can use. The problem I have found is if you do this yourself, you know what you're looking for. So you kind of hedge your bet a little bit and say, oh yeah, it does this. I've had students use this asset phenomenon tool on their phenomenon that they're selecting for a unit that they're going to be developing, and they do the same thing. So it's often best to have somebody else, a teaching partner, another colleague in a PLC, to really be objective about that. And that way it helps you fine tune the phenomenon. So those are a couple of tools that you have in your materials that will help you kind of filter your own phenomenon and check it out before you begin designing your instruction around it. There are several sites. These are three that I think are very useful, where they've posted phenomena. Many of them are aligned to particular standards. They have different examples. The ngssphenomena.com site is no longer being actively built, but it does have a range of examples there. It's going to stay live, but they're not going to keep updating it. So these sites are listed on your resource document. Sometimes it just helps to look at these and just kind of peruse them and think, oh, okay, I didn't think about that. Oh, those are some possibilities. And it may just help you come up with an idea, or it may help you find a phenomenon to use for an upcoming unit that you're going to be teaching. So again, let's pause and reflect. What are 2, 3 important ideas you want to remember about using phenomena to support students' sense making? And what are some pitfalls that you want to avoid when using phenomenon to support students' sense making? So pause the video, take a minute to reflect. And if you're working in a PLC, after each person's had a chance to reflect, share some of that thinking out. Some additional resources would be in the teacher handbook from the Open SciEd people. They have just recently updated their teacher handbook, and it's got lots of suggestions for using anchor phenomena and for managing driving question boards. One of those ways to keep students' questions visible, organizing those questions, and kind of sequencing it so the kids know where you're going and what we figured out and what we still need to figure out. Has some great resources and examples and strategies for doing that. Although the Open SciEd materials that are available now, again, they're all open resource, free materials on the web, have been written for middle school. A lot of these tools, strategies, routines are easily adapted or used just as is for either K-5 or high school. The light purple section of your selected resources document contains a link to the handbook. It's also in your resource folder, and with those pages of the phenomenon routine and the driving question board ideas noted on it. You'll also note in your folder that there's another resource from the Next Gen Storyline folks that supports the effective use of anchoring phenomena. How do we really get the most of most out of that phenomenon that we've selected? What student questions, initial explanatory models might they develop? Where do we want them to go with this? It's going to kind of be those stepping stones or breadcrumbs to understanding that phenomenon. And what might be some ways we could use those as formative assessment tools to help us kind of know where kids are, where we might need to go next, and where they are in their understanding of that. This is an example of a driving question board that comes from the Open SciEd site. And as you can see, the teacher has kind of categorized the kids' questions that were put on Post-its and got big categories. And all those categories are going back to their overarching question, that anchoring driving question for the unit. And then based on how these are categorized, they come up with some different investigations that they might do. So again, students are kind of coming up with those ideas. So one way to use that driving question board to help kids see, okay, here's where they all kind of cluster. Here's some different investigations we're going to do. And then even having a third column, like, this is what we figured out from this. So here's what we know now, going back to that overarching question, that driving question. Again, the Open SciEd material, they've got a range of driving question boards that they can show the ways teachers have used them. So I think it's really helpful to see some different ways that teachers have organized this, and even the same teacher might use it differently. Some use virtual, like a Jamboard, to organize questions. Some put them on trifold so that you have a different driving question board for each period that you might teach. Some will use different colored Post-it notes depending upon the period, so that you kind of see, we've all contributed to these ideas. But in that teacher handbook are some suggestions for managing driving question boards in your classroom, using those to kind of sequence instruction and then keeping track of the kinds of things that students have figured out. So let's recap. We've been focusing on how we can use phenomena to support student sense making. It's the why we need to know this. Understanding those big science ideas, we had to clarify those to begin with. And then we thought about the phenomena that we're going to use to get kids to that understanding. Phenomena is what drives that learning and gets the kids curious and wanting to figure out why. And in this session, we focused on two big things: determining what it means to be an instructionally productive phenomenon. It could be a phenomenon, but it just wouldn't lead the instruction where we want it to go. And then we also kind of talked about what those weren't, because I think that's important to distinguish those. And then we looked at how we can use phenomena to support sense making and making students' thinking visible, and sequencing the instruction, and ensuring that we're developing understanding of those important science ideas that we've targeted, that it all kind of goes hand in hand with each other. So once again, let's take our final pause and reflect. And if you would access your sense-making plan of action, it's kind of our running record from these different sessions, and reflect on what are your strengths and needs with respect to phenomena. What resources do you have, or are there some that you might need that would help you in strengthening your use of, understanding of, driving instruction using phenomena? And then what are some next steps, and what would be a time frame for implementing them, and how will you know where you are with respect to achieving your goals? So take a moment, pause and reflect. If you're working with a PLC, after each person's had time to pause and reflect, look across each of your plans of actions and see if there are some commonalities that you could work together as a PLC to grow in your use of and understanding of instructionally productive phenomenon, using that to drive instruction. Thank you for taking your time to work through this particular session on how you can use phenomena to support student sense making. The fourth session in this series of 5 will be about leveraging students' ideas. How do I support students in generating ideas, using those ideas and building on those ideas to support sense making in science? Thank you.